Okay, guys, let's get started. Good morning again. Bromonium ions. Here we go. We also have our outline, yes. Yellow. Anti-trans addition of halogen. That's what we're doing. It's called anti or trans. Those terms are synonymous. Trans is opposite. We saw that with alkenes. We can also have trans with like rings. That's basically opposite in different forms. Anti describes more the mechanism. Anti is also opposite. They both really mean the same thing. But the mechanism, the two halogens, is saying that the two halogens are adding to the alkene. By the way, when we say adding, we got to be careful because mechanistically we don't do this. We actually come this way mechanistically. Electrons here. But ultimately, the terminology of the halogen is adding to the alkene. Again, I don't like that terminology because it's backwards from where the arrows are moving. But how is it adding? Is it adding both possible ways? No, it's only adding in a trans manner, which is also called anti. It's not adding in a cis manner, which would be called syn. We'll hear anti and syn a little bit later. We talked about that. Mainly the reason why we get trans only and not this is why. Because the intermediate is a bridged, in this case, chloronium ion. The second chloride does not attack a free cation. If you attack a free cation, you attack from either side. Instead, it attacks a carbon and kicks one off. And whenever you do that, it's always how? Backside, or that's what we call it backside, but it may be more clear to you if you call it opposite side. Okay? Because it occurs opposite side, they end up opposite. That's ultimately why. So, we went over that below. We run out of time. We will see this as we move forward. We need to move ahead. We'll kind of repeat the same thing. Let's look at a different reaction. If you do the same reaction with chlorine or bromine or maybe an interhalogen, but include water. If you include water, the water is going to end up reacting. And you're going to end up with a halohydrin, what it's called. Specifically a trans-halohydrin, because the mechanism is pretty darn similar. What is a halohydrin? When a halo means halogen, here's your halohydrin product. Hydro, it's like water. That comes from like hydro. And the water, because water reacting, we end up with an OH. And that's called a halohydrin. By the way, look back on the yellow. With the Roman numeral 1, it gets vicinal dihalides when we add halogens. What does vicinal mean? This is actually a dichloro compound, but it's vicinal. They're next door to each other, like in the same vicinity. It's called vicinal. Didn't point that out there. This is also a vicinal halohydrin. We're really not going to see any other type, but it's because they're right next door to each other. Okay. Now note, we have regiochemistry here. We're adding a chlorine and an OH, ultimately, across the pi bond. Okay? But does the chlorine go here and OH there, or opposite? OH here, chlorine here. So we have possibilities of regiochemistry, or regioisomers. That is, but in this reaction, we only get this regioisomer. We do not get this regioisomer. The reaction is thus regioselective. It is. Why? Well, if we know our mechanism, we would be able to predict that product and not this one. Mechanism will tell us why. Let's do mechanism. Well, the first step here is just ignoring the water. When you have halogen and an alkene, you're going to get the same kind of outcome. It reacts reacts first. We have the chlorine. We're going to leave cation, left or right? Correct. On the left, we attack the chlorine, kick that one off, and that's going to give boop, boop, boop. Now bonded to chlorine, but we made cation here. And we formed what? Cl minus. Okay, let's assess this. Is this really formed, or is something else going to happen at the same exact time? It's going to back bond at the same exact time. These electrons are right there. Aren't they going to be attracted to the plus?
Yeah.
They're going to come in here and back bond. And that leads to what? Boop, boop, boop. Chlorine only has 2 lone pairs, and that is a positive charge. So, is this really formed? What do we know? It's not actually formed. This is just how Stevens does it on the board. Both of these steps happen at the same time. Here we go, same time. You bond to me. Boom, chloronium ion. There was no intermediate. It went from chlorine. This is the first intermediate. Okay, what attacks it? Chloride could, but like we said, if you got water, it's going to attack. Now we could argue about why. A lot of times when you do this, you do use a good amount of water, so maybe it's just excess. Where's water going to attack, left or right? It's the same as before. And the answer is really the same as where you would have formed cation. So the answer is already on the board, right there. But why? Because the chlorine pulls, okay? Chlorine's very green. 3-member green, guys. 3-member green. I'm the chlorine, but I can pull. But which one am I going to pull more on? You, because you have a rich friend. And so you don't mind being positive. So it pulls more on you because you have rich friends. So this carbon ends up being more partial plus. Again, the answer's right here really, but it ain't a free cation. It's a bonded thing here. And water attacks, these electrons attack here and kick that off. This positive chlorine is serving as a leaving group. Now if we had stereochemistry, this would be backside. Well, it is backside, but we're not really looking at stereochemistry here. We'll point out why in a minute, maybe. What does this give? Well, it doesn't get the product yet. It gives boop, boop, boop. Chlorine just kicked off. It got its 3rd lone pair back. What's now bonded here? Oxygen with 2 H's. We have not lost an H. The H's here don't just magically disappear. Now we have to look at removing an H. Every step is stepwise, unless we say it ain't. For example, that wasn't stepwise. How do we get rid of this? What can take the H? Actually, the Cl minus. Floating around here, Cl minus can take it. Take the H, leave the electrons behind. What does that give? That gives that product plus what? What is the small molecule byproduct? ACl is also formed in this reaction.
Can I put water attacking the iron?
Yes, you could, because how does HCl exist in water? You learned in Gen Chem. You put HCl in water, what do you get?
H3O.
You get H3O plus Cl minus. That's how it exists in water. This is in water. So how is this really going to exist? Like this. You could get here directly by just using water. If water took this, you'd form that, and the Cl minus would just stay there. That's actually strictly more correct. But then if someone says, well, HCl's formed that reaction, right? You wouldn't understand. You'd be like, where's it? So you just have to deal with it and understand that. Thus, if you did this reaction, at the end, it would turn litmus paper red. Well, practical information, yeah? Generated acid. Very similar to the previous mechanism, except water attacks instead of chloride. Whenever you have water, it's going to attack. We didn't do any stereochemistry here. It is backside attack here. But it's really not relevant to consider stereochemistry. Why? Look at this product. Does that product have any stereochemistry? That is there another way to draw that product? What if we draw the OH between the two methyls like I did here? Because I know some of you are like, why is it drawn between the two methyls here, but here it's drawn like that? Does that matter? No. That carbon is not chiral. That means there are no different projections. There are no possibilities. It's like if I showed you this here and said, okay, show me the right-hand version and the left-hand version. You'd be like, what do you mean? There is no right or left-hand version. But if I showed you this, you would know that there's a right and left. This is a case where there is no right or left. There's no way to show that. As long as you have a carbon with two methyls and OH and that's it. There's no other way to show it. Draw them together however you want. That's also not chiral. That product has no stereochemistry. There's no alternative way to show it with different projections. So that's why I'm really not concerned with stereochemistry in the example. Later on, we'll do some that do have stereochemistry that we need to just look at. For example, down here. Now, some books will talk about what do we formally add to the alkene? HOX, HO chlorine. But I like to just consider it water and whatever. It's all just different terminology, different things people like to say about what just took place. What about bromine in water? Now, when you have rings, you often have stereochemistry, more likely to have stereochemistry. That's really not a good statement. Actually, the statement is, with rings, the stereochemistry is easier to handle because you don't have free rotation. Because you don't have free rotation, things are more fixed. And at the beginning level, that's just easier to deal with. So, forget stereochemistry and just draw the product without it. Okay, whenever you do predict the products, you do have to have a little bit of memorization. A little bit, like a note card. You got an alkene, you got halogen and water. What's going to be the product? Yes, halohydrin. So that's where you have to know to get started. A little bit of memorization. But then your mechanistic knowledge kicks in. Okay? It's a mechanism for this. By the way, up top, somebody asked about a reaction coordinate diagram. I already erased it, but let's see if we can draw one real quick for the mechanism we did up top. We have some type of energy. We have some type of reaction progress. Up there, the alkene is A. We'll put A some arbitrary level, yeah? What was the first intermediate up there? How many total intermediates were in that reaction up there? Total intermediates up there. How many intermediates were in the top reaction? Answer is 2, correct?
So one didn't form.
Why is that difficult? Because didn't we draw 3 structures between starting and end? But one of them we said was not actually formed. So since it's not actually formed, we don't count that one. The remainder was 2. What were the 2? The chloronium ion, but then there was one after that was what? It was basically final product, but it was still protonated. Well, that's an intermediate also. The first intermediate is chloronium ion. How does it compare to the starting? It's higher. It's an ion. Okay? That's B. B is the chloronium. We're skipping that first thing. You remember the NAF thing? That doesn't exist. We only drew that on the board. It does not exist in real life. That's the chloronium ion. What came next? The protonated oxygen structure. How's that going to compare to this? It's actually going to be a little bit lower. It's still an ion, but it's lower. The reason it's lower is because everything has an octet. Well, that doesn't work here because in the chloronium everything has an octet. It wasn't a carbocation. Chloronium, everything had an octet. It could be a little bit tough to assess. It is lower. Typically, your initial intermediate is your highest energy thing. Doesn't have to be, but in most of the reactions we'll look at it is. The other thing, the chloronium ion is a three-membered ring. So it's got some strain. Not only does it have strain, okay, we had stuff here. Not only is it strain, but you got a chlorine that's positive. You don't like being positive. You might even ask, well, why did it even want a back bond? If the three-membered ring is bad, and chlorine doesn't like being positive, why does it even want to do this? Well, it can't get away from a basic physics principle of negatives like positives. It's got that Coulomb attraction. And whenever it back bonds, you are making a bond. And typically bonds are good. The bad thing is it's a strain bond, and it's plus. But it's a high energy intermediate, and when we open it up, when something comes in and opens it up, that is going lower. Then after this was what? Final product. How does final product compare to starting?
Higher energy.
Lower energy. We started with a pi bond, we made 2 new sigma bonds. You can get your calculator out. What bonds were broken? Pi bond. What bonds were made? Sigma bond to O, sigma bond to chlorine. That's 2 sigma bonds. Those are going to be stronger than the pi bond you broke. It should be lower energy. You can prove me right or wrong with your calculator, and you should be able to do that. I'm going to say it's lower, and we're going to call this D. So I'm going to make it lower. Here we go. Boom. Transition state energy leading to this. Now we got to have a transition state leading to this. But it ain't going to be too high because now we're falling downhill. Just a little bit. This needs to really come to a well because to get here, we don't just keep going. We have to have some little transition state to get here. Small transition state energy. Any transformation has some transition state energy that's going to be requires some. There we go. There's your rate determining step. Formation of the chloronium ion. There you're falling downhill, right? 2 intermediates. Okay, let's do this one down here. Bromine and water. If we didn't have any stereochemistry, let's just show up with no stereochemistry. We would have, okay, bromohydrin. We're adding a Br to one and an OH to the other. Is the Br going to be on top or bottom? This is the type of thinking you need to be doing when you see this. Br is going to be on the... Yes. Yes. Because cation is going to be on the top. Now we know it's not a cation that water attacks, but it's the same place. So water is going to attack the top. There's a methyl up there. This loses an H, and there's bromine. There's your product with no stereochemistry shown. This is just regiochemistry. Okay? Again, I'll do it. That is, I'm not going to do full mechanism, but what's the first intermediate here? Bromonium ion. Now the bromonium ion is going to look like this, methyl here. If I drew this bond forward, this would be back. This is where the alkene attacked the bromine, kicked the other one off. We made cation, right? Cation here, but then it back bonded. But if the first bromine was forward, when it back bonds, that bond's also got to be forward. But we could also have had the opposite. We could also have had this bromonium ion. Because the alkene could have attacked the bromine sort of this way, back. Made bond to bromine, cation. And then when this bromine back bonds to cation, you now have 3-member ring going back. But that's actually going to push the methyl forward. We'll do more of these and we'll talk more and more. But it's tetrahedral now. These two carbons are tetrahedral. They start at trigonoplanar. 2 in the plane, 1 forward, 1 back. 2 in the plane. What's forward here? Undrone hydrogen. Okay. Then, let's just look here. Water attacks, top or bottom? Top, right? So it comes in here. It works its way in here and kicks off the bromine. How does the water come in? If the bromine is forward, how does the water come in? Back. Okay? 2 arrows because I'm going to skip one intermediate. I'm just going to go ahead and deprotonate it. This just opens up. It's still forward. The water came in back. Okay? I went ahead and deprotonated it. I skipped the intermediate, right? By default, the methyl is now what? The methyl is now forward. By default, but also what happens is the methyl is back, the bromine is forward. Okay? Someone come do a backside attack. Here's the bromine with the marker. How are you going to attack me to kick off the bromine?
This is the bromine?
Yeah.
So we're going to do that side, right?
You got to attack the carbon, not the bromine.
Okay, which one's the target?
I'm the carbon.
Okay, you.
From which way though?
From the back.
Well, but really opposite this. So you need to
This
be
side.
there. You go. Opposite this. Okay, attack me. Well, no, you got to attack me. I'm gonna throw this to you. Never mind. It's over. It's over. You attack and kick this off. But this gets kicked off. But when you attack, this moves forward because you're coming in and you're pushing this forward.
Yes, that is what happened.
It can't. Two things can't have a bond angle of 10 degrees. Forget about this. You attack. That gets kicked off. But this gets pushed forward as you come in. As that thing comes in, it pushes this methyl forward. Also, by default, if that's back, this has to be forward. That's how we get to this. Here's your product. And ultimately, the two things that have added across the alkene are what? The two new things are trans at the very top. Trans. There's your product. But hold on. What type of stereochemistry does that product have? A good bit. You got 2 chiral carbons. This is chiral. In all the reactions we're going to do, you're always going to get the enantiomer. Until we say something different. Can you draw the enantiomer of this? Yes, the enantiomer would be where everything is switched. If you look in the mirror, everything is switched. All R's become S's, all S's become R's. If you look in the mirror like this at home, your mirror image is going to have its left hand forward and its right leg forward. Opposite of what I have. Everything is switched. The enantiomer is going to be OH methyl plus enantiomer. This plus enantiomer. This is the enantiomer. We'll do more of this. How do you get the enantiomer? The enantiomer comes from water attacking here. Top. The bromine is going back, so how's the water going to attack? From the front. Opposite of the bromine. If it attacks from the front, it'll be a bolded OH. It pushes the methyl back. And when this just opens up, nothing changes here. That's how you get the enantiomer. You get both outcomes because here you had both. Okay, we included stereochemistry there because it needed to be. You get enantiomers. We'll do more examples moving forward. You have examples down here to do. Please try those. And we need to start more and more thinking about stereochemistry. This is just interhalogen, ICL. This is DCl. Deuterium, it got cut off. Deuterium is an isotope of hydrogen, right? Anytime you see D, it's the same chemistry as H. But it's going to be a D there. And usually instructors or tests like to use D because it allows for stereochemistry. Because if I have a carbon with two H's, it's not chiral. Assuming everything else is different. But if I have a carbon with an H and a D and two other things, it can be chiral because D is different from H. So it allows for stereochemistry. That's why it's often used. But when you see it, this is just HCl. Just draw it as a D. HCl, that goes back to our very first reaction, right? Okay, next on the outline as we work our way around on the yellow is synthesis of epoxides. An epoxide is a three-membered ring with an oxygen. Formal name is oxirane, but nobody calls it that. It's called epoxide. Three-membered ring. In terms of functional groups, it's actually an ether. The oxygen is bonded to two carbons. It's a cyclic ether, three-membered ring. These can be made. You may have heard of epoxy glues. It's an epoxide that can be polymerized and turned into a glue. In organic 1 here, we'll learn how to make epoxides. You'll typically then react them in organic 2. But they're typically made from alkenes by reaction with a peroxy acid. This is condensed for peroxy acid. Here's more of a structure. If that was only one oxygen, that would be a carboxylic acid. With 2, it's called a peroxy acid because the OO linkage is often called a peroxide. Your simplest peroxide is hydrogen peroxide. So this is a type of peroxide, but it's also like an peroxy acid. Condensed, okay? The most common peroxy acid is this one, where the R group is this benzene ring with a chlorine, so-called meta to this group. It's called metachloroperoxybenzoic acid. It's in your textbook. Most people just say MCPBA. It's the most common peroxy acid. So you can see this like that, like that, like that, etc. Let's look at mechanism. The peroxy acid, the two oxygens are actually polarized. Two oxygens. Well, we just got through reacting with like two bromines. We have two oxygens. We talked about schizophrenic up here, and that's why it became polarized. The two oxygens are permanently polarized because one of them is bonded to this carbonyl. And this oxygen is pulling, that means there's pulling this way, and it's all being pulled towards this. That leaves this oxygen over here partial positive. And the alkene attacks that oxygen. These electrons kick the other one off, just like attacking this and kicking that off. Where are we going to leave cation, left or right?
Right.
On the left, correct? So does this arrow movement give this? Bond to O, and there's an H on the O. So bond to OH. We kick that off. That became what? Third lone pair on the oxygen. That became this. Okay, what do you think about this structure? I've already told you the answer. Got a cation, but we got this new group of a lone pair right next door. Is it just going to sit there, or is it going to do something? It's going to back bond immediately. So this is not actually formed. First two steps are concerted. The first intermediate is this right here. This is very similar to like a bromonium ion or chloronium, right? The big difference is this can go neutral by losing an H. That can't go neutral by losing an H. This has to be further chemistry. Something comes in and gives it its electrons back. So you get further chemistry. Here you just get acid-base chemistry. And this guy, anion, can take the H, leave the electrons behind, and when you do, what do you get? Get your epoxide. Which again is a lot like the bromonium, but since it's neutral, it can be isolated much easier. And there you go, there's your nice neutral product. Now the key point is, do you see the similarities in the mechanisms? And the other mechanisms we're going to look at are also going to have the same similarities. Yeah? I hopefully see the similarities?
There's one intermediate in this one, right?
Good question. There's only one intermediate. It's this guy right here, right? That's not really formed in real life. That's just Stevens showing it on the board to help us see things. That's the end product. Yeah, there's only one intermediate there. That's called an epoxidation of an alkene with a peroxy acid. Examples below to work. If there's no stereochemistry involved, by the way, what is dichloromethane in this reaction? Just solvent. Most reactions involve a solvent. You used dichloromethane yesterday in lab, right?
Mm-hmm.
Did it react in the mechanism? No. By definition, solvents don't react. And when they do, we sort of make note of it. But the thing is, though, you got to get used to sort of recognizing solvents. Otherwise, you're like, what's that for? It's a solvent. So I'm just throwing that in there. So next time you see it, you won't be confused. Okay? tomorrow night you're doing a study section or something and somebody shows you a solvent, you won't be like, what's that? Right? So, what's the product there? Well, in terms of just what's being done, we're adding an oxygen across the two carbons of the alkene. Boom, 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 boom. Used to be alkene. Let's just bond them together with oxygen. So that's sort of the simplistic starting point. Then, of course, mechanism, but also stereochemistry. Is there any stereochemistry in this to consider? Is that carbon chiral? No. What about that one? Yes. 4 different things to text.
Yeah.
Okay? So if that means we can show 2 different projections, like R and S. 2 different projections may have this bond forward or back, or that bond forward or back, or whatever. Which way you want to draw it? Anybody else? Answer is both. Because like I said 10 minutes ago, check the tape. Every reaction we do is going to have an enantiomer, when possible, right now. Unless we say otherwise. How to show this? There's different ways to show them. Here's one way. We can show this like this. Now your book will say like plus an enantiomer or something. The enantiomer will be there you go. There are your 2 enantiomers. We'll continue to talk about this. You may be wondering, well, mechanistically how? Well, sit down and try to do it. How about R and S? Let's do R and S. What do we got here? R and S. R? If that's R, I'll bet you a steak dinner that's S. I don't even need to look over there because I know I reversed it. Backbone's the same. Is this R? Look at this carbon, right? The carbon. Oxygen's 1. What's 2? Carbon with oxygen or carbon with carbon? Carbon with oxygen. So this is 2. This is 3. What's 4? The H is going back. 1, 2, 3. Clockwise, correct? R? Yeah. If you do that one, that one should be S. Okay, other ones for you to do. Rings are a little bit easier to see stereochemistry. We did an example before. See how you do. So it's actually better for you to try first, then we discuss, because then you can learn from my discussion. Rings are easier. These 2 are a little bit more challenging because the product's going to have 2 chiral carbons. That product over there only had 1. Because the other carbon of the original alkene was not chiral. When they're both chiral, in any case, it's a little more difficult because then not only do you have each individual, you also have the relative stereochemistry. How they're projected to each other. These down here. First off, if we didn't do stereochemistry, this product would be boom, 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 boom. Between the 2 carbons here, an oxygen, there you go. But both of these are chiral. Let's forget about individual R and S. How are these two groups related to each other? Because this is a ring with two groups. Remember before when we had a ring with two groups, such as this? These could be cis or trans. Well, that's a ring with two groups. Are they cis or trans? Should they be cis or trans? Okay, here's how you should do this, and then you will give these a try. Think about it. I recommend when you do these here, where it's going to end up with both two carbons in the product, first thing you should do is turn this alkene. Okay? Right now it's all on the plane. Turn it and make it become, first off, are the groups cis or trans in the alkene? Trans, correct? Trans alkene? Okay. Show them trans here. More specifically though, like instead of them being flat, here it is, my thumb is flat on the board. Show it either forward or back. Show it like this. And now my thumb is forward. Let's draw this maybe like this. Okay? It's the same compound. I'll draw it on the paper. Boom, 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 boom. Here it is on the board. Now when I turn it flat, look at this methyl here. I'll put my fingers here. When I turn it flat, does it go towards you or away from you? Towards you. But look at this group. When I turn it that same way, how does it go?
Back.
It goes back. That's all I've done. I've just turned it, so now I have projections. Now do the reaction, and it will make your life feel so much easier. For example, let's go ahead and do it, and then you can do the next one. What's the mechanism? It's easier to do this, but okay, let's just here. This attacks. Now here's where I'm going to have to just combine everything. And at the same exact time, what does this lone pair do? Back bonds. See, if I did this originally, you guys would have been lost. It's attacking, but at the same time, this is attack. You back bond. Okay? As drawn, this is either top or bottom. Right now, this is occurring from the top. Okay? That is, I turned it like this, and now the methyl's forward. Now the alkene comes up and attacks the oxygen, and the oxygen back bonds immediately. But all this is up. And the product is, I'm just going to draw that flat, and draw this here, I can draw this here, but the oxygen just goes like that. Because the alkene attacked the oxygen straight up, and the oxygen straight up back bonded straight down. And there you go. We lost the H here as a second step. There's your product. And the two groups are what? Trans. They're trans. Now, why did I only have the alkene attack up? Could the reagent have not been below? The alkene attacks the oxygen down, and the oxygen back bonds from down. That would give us what? That would give us, now I'm just going to draw these forward, but I'm just going to push them up a little bit. Still forward. That would give us this. This is where it came in from below the plane. What's the relationship? First off, both of these are trans.
It's the
What's the
same.
relationship between these two?
It's the same.
Enantiomers. Those are mirror images. You can show them as mirror images. You can do R and S. They're going to be, one's going to be RS, the other one will be SR. Remember I told you we're always going to get enantiomers. You get enantiomers because it's both top and bottom, 50-50. Try the one below it. What's the first thing I suggested doing with this guy though? Redraw it. Once you redraw it, your projections are already there. Most books will not tell you to redraw it. They'll tell you to do this and then figure it out. Free information here, guys. Of course, do whatever works for you. I'm telling you what works for me. Anytime I do this, I turn it first. And then the new stuff, I put in the plane. The new stuff, I don't do projections, because it's in the plane. See, that was not forward or back, it was in the plane of the beam. Next reaction. We'll have to just introduce this. Next reaction is another three-membered ring. There's no oxygen. This is actually a cyclopropane, all carbons. You make these from alkenes, different reagents. In this case, we're using this here. It's called diazomethane. Okay? Diazomethane is actually a little explosive, hard to handle. We will not be using it in lab. But it's fine on the board, right?
Yep.
Here's a Lewis structure for diazomethane. You cannot draw it without charges. This takes a little heat. Delta, heat, universal sign for heat. With heat, this thing will break apart. The nitrogen is positive. It would like electrons. With heat, it just sort of ionizes. Well, it's already ionized, but it sort of doubly ionizes. These electrons move on to the nitrogen. With heat, we generate this guy plus nitrogen gas. This is CH2 with a lone pair. That's actually a neutral charge, as I think was on test 1, page 1. It's neutral. This thing is neutral. Neutral becomes neutral. That's neutral, this is neutral. So why am I showing charges? That's because it has dual character. It's missing a bond, so it's almost like it's a cation. But it also has a lone pair, and that's almost like it's an anion. It's net neutral. It's an atypical carbon. Usually we said atypical carbons are going to be charged. Well, this is actually neutral. It's called a carbene. Carbene. We'll have to pick up here. The mechanism is very similar to the previous mechanism. Please take a look. Please take a look. Have a good day, guys. See some of you this afternoon in lab. Upstairs. We'll get started at 2:30.